All right. So last class, we talked about squaring the graph. Actually, even before that, we said graphs with high spectral gap or small lambda are easy, right? So if a graph had small second largest eigenvalue, small small being bounded away from 1 by a constant, then we were good, okay? And then we started thinking about operations to improve the spectral gap, right? Maybe you start with a graph, which is not very good, but I can massage it, change it somehow to make it a good graph, and then solve the problem on the good graph with the hope that it's kind of a reduction. You solve it on the good graph, you still solve it on the old graph, right? And to this end, we started looking at operations like squaring the graph, right? Squaring the graph just meant that you're literally just taking the square of the adjacency matrix. And the graph theoretic interpretation is you're kind of short-circuiting hops of length 2. You take 2 steps, and wherever you land, you put a direct link between them, okay? This could potentially lead us to multi-graphs, but everything carries over as it is. And today is when we are going to really look at this beautiful and highly impactful idea called zigzag product, okay? And then we will see analyze spectral properties of this. Okay, so in some sense, we are going to put the main problem, that of solving connectivity with small space, on the back burner for this lecture. We will kind of study a zigzag product as on its own, and arguably, its influence is much greater than just helping us solve this problem. And then in the next lecture, we'll see how to use this tool to come back and solve the ST connectivity problem, okay? And finally, I'll hopefully say a few words about the special graphs called expander graphs. All right. Okay. And let's get started. Okay. So the definition will be somewhat, this color always gets me. I think I showed it to you. All right, so zigzag product is, as a name, it's a very good name for what it is. But to get there, we need to set up some notation. The definition will be easy. The analysis will be more complicated, okay? All right, so it's an operation. You should think of it as some kind of variant of multiplying 2 graphs, whatever that means. We multiply numbers, we multiply matrices. Now we're going to talk about multiplying graphs in some sense, okay? So we need 2 graphs, and we will combine them to create a new graph in some way, right? So we can do this operation under some consistency conditions, right? What does that mean? It's like saying if I have 2 matrices, I can only multiply them if the number of columns of the first matrix equals the number of rows of the second matrix. That's the only case where matrix multiplication is well defined. In the same way, zigzag product is well defined if you have some kind of consistency, okay? Consistency in the parameters. So let's say I have a graph G, which is a N, D, some graph, some lambda G. Okay, recall our notation. For us, the most important things in a graph are the number of vertices, the degree of the graph, and the second largest eigenvalue, right? Which I'm denoting lambda G by lambda G. So the definition doesn't care about what lambda G is, but let me just put it there as a placeholder. And then we need another graph H, which the number of vertices in H has to be the degree of the first graph. You should think of G as kind of the main graph and H as kind of the small graph. So you're combining a main big graph, a small graph to create a new bigger graph, right? So the number of vertices has to be the degree of the first graph. Right? As I said, it's in some sense, just as for matrix multiplication, you need the columns to equal the rows. Here, you need the degree of the first graph to equal the number of vertices of the second graph, right? When these two things happen, we're going to define an operation and get a graph, which we will denote G zigzag product of H. This is the notation. G with a circle Z in between for zigzag H. This will be a new graph. The number of vertices will be n times d. Okay? Product of the number of vertices in both graphs. The degree will be square of the degree in the second graph. And lambda will be something that we don't yet know. Okay? So this is the sort of syntactic definition of what zigzag product is going to be. A big graph, a small graph, and then gives you an even bigger graph. But the degree is kind of inherited from the second graph, right? So that's an important point. The degree of the new graph is inherited from the second graph, all right? Okay. And lastly, the easiest way, the cleanest way mathematically to define zigzag product is to use something called rotation maps for graphs, right? So what are rotation maps? But to define that first, I need to talk about consistent labeling. Okay. So if you think of rotation maps or consistent labeling is just some standardization about how you're going to refer to the edges of the graph, right? So you have to fix some labeling of the edges of the graph so that you can say, okay, this is edge number 1, edge number 2, and so on. And once you have this, we're going to define how to do the operation. Okay, so formally, suppose I have a graph which is a d-regular graph, right? So imagine this is my graph. It's a 2 regular graph, just a 6 cycle, right? I have vertices 1, 2, 3, 4, 5, 6. A consistent labeling is just a way to label the edges so that, so something like this. I call this A, B, A, B, A, B. So it's a labeling of the edges so that for every vertex, all of the outgoing edges are distinct. I don't want any ambiguity around here. If I say take edge number A out of vertex 1, you know what it is. There's no ambiguity. There are no two things which are the same label. Okay? Because I'm going to say take edge number A out of vertex 17 and then take edge number B out of vertex wherever you land and so on, right? So we don't want any ambiguity. So a consistent labeling is a mapping L from edges to the degree of the graph. Okay, it gives each edge a number from 1 through D, which I mean, here I used A and B to kind of distinguish from the names of the vertices, but from 1 through D, such that at each vertex, all edges at the vertex have distinct labels. Okay, we'll consider a slight generalization of this later on, but for now, this is enough to understand the basic definition of zigzag. When we have to do the analysis, we have to slightly, consider a more complicated definition. Okay, so this is a consistent labeling. There's a question, what does D mean? This is just the set 1 through all the way up to D. Okay. All right. And okay. Any questions about this? So just saying I want an enabling of the edges so that at every vertex I have distinct labels, and I basically use the degree of the graph as the number of labels that I have. Okay, so now what is zigzag product? How do you define it? I'll first draw some pictures and then define it formally. To define it formally, we need a slightly more complicated definition of consistent labeling. So suppose I have some graph, right? Let's say okay, so let's say this is my graph. Typically, you do it with more edges, but the pictures will get complicated pretty soon. So let me keep it simple. And okay. So this is my big graph G. And actually I want the degrees to match. So let's say I have this. So let's say this is a 4 regular graph. Maybe I'm not drawing all of the vertices or the edges. Some are missing, but that's okay for now. And then we have H, which is just the 4 cycle. Okay. So this is G, this is H. G is a 4 regular graph, meaning it has 4, 4 edges coming out of every vertex. Then I can do the zigzag product. Okay, it's well defined. How do I combine them? The first step is you should imagine replacing each of these vertices in G with a copy of H. Okay? So each of these vertices will now get expanded like a mini cloud, which is exactly a copy of H. All right? So it'll look something like this. Okay? And so on. So first step is every vertex of G gets replaced with a copy of H. Okay, like a mini cloud. And then you have to define the edges. We'll do that in a second. So something like this, right? So we have this guy. Actually, just think of this as like a cloud. They're well separated, and I'm going to connect these vertices in the cloud. So how many vertices do I have now? I had capital N vertices in G. Each one is getting replaced with a copy of H. So the total number of vertices will be product of the number of vertices in both. Okay, so that part is what we already have. Okay. The copy or cloud of edge. Okay. So now what is the degree going to be? So I said the degree of GZH is D1 squared, right? So this was at the beginning. I said it's going to be a graph where the degree is the square of the second graph's degree. Okay. And we'll think of D1 squared as basically a pair of numbers, one from 1 through D1 and the other from 1 through D1. It's like two labels for edges in H. Okay. So this is some number K1 belonging to 1 through D1, let's say, and then K2 belonging to 1 through D2, sorry, D1 again. And so every edge in this out of a vertex, you should think of it as corresponding to a pair like this, K1 comma K2. Okay. So how do I define these edges? So I'm going to label these vertices in this expanded clause in a natural way, right? So first I'll say, maybe this corresponded to vertex V in my original graph in G, and these are A, B, C, D, right? So this is A, B, C, D, right? So the vertices in the new graph, I can index them as saying, okay, they correspond to vertex V in G and vertex A in H, right? So how are the edges going to be? Edges in are as follows. Okay. So just imagine I'm at one cloud. This is V comma A, V comma B, V comma C, V comma D. All right. So what do I do now? So starting from here, the edge corresponding to K1 comma K2, where does it take my vertex V comma A? That's how I'm going to define it. Okay. Given any pair of numbers 1 through D1, comma 1 through D1, K1 comma K2, I'm going to draw an edge out of every vertex. In particular, let me focus on this vertex V comma A. Where does this edge take me to? So it'll take me to something like this. It's kind of a weird definition. Weird in the sense that it's very clever as to why they define it this way. It's kind of magical, but it works, beautifully. Okay. So you take 3 steps overall. The first step is going to be within cloud. So in this cloud, I'm going to take a jump according to vertex K1, according to the label K1. Right. So what does this mean? So recall, H is a D comma D1 graph, right? So every vertex in D has degree D1. So given K1, I can say go to whatever the label of K1 takes you to. Okay. So let me, maybe use this color for jump initiated by a H step. Okay. So given K1, it's a number from 1 through D1. It says, okay, if you're in vertex number A, take edge 1 out of it. So I take this edge, I end up here. So within cloud step, right? Now I'm going to take a jump across clouds. But how do I decide where I end up in? So there is a different way of interpreting the vertices in H. Okay. So remember the vertices in H, Mohan has the exact idea. The vertices in H, the number of vertices is exactly the degree of G, right? So there is a correspondence between vertices in H and edges coming out of vertices in G, right? So if you go back here, this is a little bit like saying, maybe I label this A, B, C, D, right? Because this is degree 4, which is also the number of vertices. So there is a correspondence between the edges in this graph and vertices in H, okay? So what is the across cloud step going to be? You'll say, well, after taking the within H step, I'm at B, right? So now I'm going to take an across cloud step corresponding to edge with label B out of vertex V in G. Okay, so I'm going to take an across cloud step and say, it's like saying if I'm here, V, maybe this is U, right? If I take vertex label B, I go to U. So I'm going to the cloud corresponding to that vertex. Okay, and where do I end up in that cloud? At the exact same spot. So if it was, if this is the cloud for vertex U in G, where do you think? So where do you think this edge should take you to? Various options, but take some guess. It's somewhat natural, yeah? UB, exactly, right? So this is UB. Okay, so this is the across cloud step. And then what should you do? Again, take a guess, because we have used K1. So all of this is just determined by what K1 is, right? But we still have K2. So what should you do? Take K2 in that cloud, right? So you take one step within this cloud, jump across cloud, and then take a step inside. So that's why it's called zigzag, like, so the picture didn't do justice, but it's supposed to be you're zigging here and then zagging over there, something, yeah? K1 and K2. So K1 and K2 are numbers from 1 through D1, right? Which is the degree of H, right? So if my degree is 1 through D1, then if I say take vertex edge number 10, then it means that my vertex, I have 10 neighbors or something, I'm going to take that labeled edge, okay? We'll make it formal and see an example soon too. But I just want to give this picture of taking a within cloud step, a cross cloud step, and then within cloud where you landed. Okay, so here you had U comma A, U comma B, U comma C, U comma D, and then you take a within cloud step. Maybe this is what K2 takes you to. Okay. So after doing the zigzag everything, then the real edge that you add is this guy. So this is the edge that you add. You don't keep any of the original edges, you just add these edges. Okay, so one K1, one across, one K2, and wherever you end up, you connect them. Okay. Any questions about this? Yeah? Yeah, we get rid of everything. So only edges which will remain are these purple ones, right? So these are we only keep these. Like, we are generating them by using these, but in terms of actual connections, this is what we have. And you should think of this purple one as having the label K1 comma K2. Okay, yeah? Within ones, yeah. There are variations where you don't, but I think removing them is the best, because that way you'll get the degree to be exactly D1 squared. and everything is kind of clean and you can repeat it. Okay. Every single vertex. Every single vertex and every single pair K1, K2, right? So for every vertex and for every K1, K2, I add these edges. Okay. So let me just write that down. So for every vertex V comma A and pair K1, K2 belonging to D1 times D1, take a within cloud step according to K1 in V cloud. Okay. And suppose you get to V comma B. Take edge labeled B out of V in G to get to U. So you jump to U comma B, right? And then take edge labeled K2 to get to, maybe U comma B prime in U cloud. Connect V comma A, U comma B prime with edge label K1. Okay. So, so that's why this consistent labeling is important, because you need to know which number corresponds to which edge in both of them, right? Okay. And it's also easy to see that you're essentially getting a consistent labeling for the new graph, except there's a small twist, but we'll talk about that in a second. Any questions about this? At least the basic definition. We'll see a quick example and then the formal definition soon. Okay. All right.
I don't know, can you hear me?
Yeah.
Sorry, just a quick question. So for like the K1 and K2 steps, we're using also a consistent labeling for the smaller graph.
Yeah.
Exactly. All right. Thank you.
Yeah. All right. So, I have these pictures drawn up, but I don't know if I can copy them that easily. Give me 1 second. Software is very good, but when the board gets very big, it starts complaining and becomes very slow. Where am I? Okay, it's not letting me copy for some reason, but I can definitely draw it quickly. So this is going to be our G. And so it's again going to be degree 4. So this is our graph. It's a multi-graph, but it doesn't matter. It's degree 4, and we need a consistent labeling for it. So we'll say this is a consistent labeling, A, B, C, D, B, C, A, B, B, C, D, A, B, C, D, A, B, C. Okay. So this is a consistent labeling for this graph. You can check that. And this is G, and H is going to be the same old 4 cycle. Okay. And here, the degree is 2. So this is my consistent label. Okay. So now GZH, how many vertices will it have? 6 times 4, 24. The degree is going to be 2 squared and then something graph. Okay. And I will draw one edge and that's it. Okay. Actually, I'm not kidding. You can actually code it up. I did it at some point. You can generate billion vertex graphs using this in like fraction of a second. Right? If you're slightly clever about data structures, you can easily do that. Okay, so these are my 6 clouds. Total number of vertices is 24. Now I have to define edges, right? So this is cloud 1, cloud 2, cloud 3, cloud 1, cloud 2, cloud 3, cloud 4, cloud 5, cloud 6. Okay. And so let's say, I'm here. I'm in 1, 8. This is the vertex. I'm going to try and figure out its edges, right? And the edges should correspond to pairs K1, K2, right? So let's say, where does 1, 1 take me to? Okay. So where would 1, 1 take me to? So let's work through that. So first, I need to do a K1 step in the cloud. Okay. So what does this mean? I should go from here to here. Okay. And then I have to jump across clouds. But how do I jump across clouds? I should take a jump in G according to the vertex indexed by the copy in H, right? So here it's label B. I go here. Where is B taking me to? All the way here, right? So I jump here. Okay, this is the across cloud step. And then 1, 1 is taking me here. Okay, so the 3 hops are done, and then I connect the 2 endpoints. So I get this edge. Okay, the purple one is the real edge. The others are kind of going to the construction. All right. And in the same way, if I do maybe, let's see, let's do maybe 2, 1. Again, from the same vertex. If I'm doing 2, 1, I need to first take this 2 hop. So I go here. Right? And then that's vertex number D. Where does D take me to? It takes me to this cloud. Right? So I jump across. And then number 1 takes me here. Okay, so I'm going to add this edge as well, right? So the purple edge, again, these two purple edges will survive. The rest are just kind of only for calculation. So that way, every vertex will end up having 4 edges, 1, 1, 1, 2, 1, 2, 2, 1, 2, 2, and so on. Okay. The end of the day, you get something which looks weird, but the degree is still 4, and the number of vertices is 24. Any questions? Yeah. Mm-hmm. You have to fix it. To define the thing, you have to fix it. It can change based on how you're changing the, in this case, you'll probably get something isomorphic, but not in general. Okay, this cycle is very symmetric, right? It depends on the labeling, actually. It's really depends, it's not just a function of G and H, it's actually a function of how you're labeling those things, okay? So this is a picture, we'll make it formal in a second as well. It's when you write it down formally, that's where you see it's just 3 equations, so computing it is actually very easy, okay? All right, okay. So how do I make it formal and so on? That's a good question. It's not like it really does depend not just on what G and H are, but also on the labeling, okay? So to make it formal, we are going to use this classical notion, which was around for a long time in graph theory, but not as widely used. It's something called a rotation map. Okay. So what is a rotation map of a graph? It's an extension of consistent labeling, right? So the reason we are going to extend is, once the first time you define it, if you have 2 graphs which are consistently labeled, zigzag is well defined. But if I want to recur, somehow maintaining consistent labelings is a little bit trickier than maintaining rotation maps, okay? So what is this rotation map? Suppose I have a graph which is D-regular and has n vertices. Then a rotation map of G is a mapping from vertices and a number corresponding to the degree of the graph. Okay. So it takes a vertex, an index of a potential edge label out of that vertex, gives out a new vertex and an edge label for the where you end up. Okay, that's the interpretation. It's a mapping from n times d to n times d, right? And rotation v comma I equals w comma j if the ith edge out of v n set w and is the jth edge out of w. Okay, so what does this mean? So just imagine the adjacency list representation of your graph, right? So if you think of the adjacency list representation, from vertex v, I will write down the neighbors of the vertex v, okay? And what it's saying is, if I pick the ith element here, I'll get vertex w. Okay, so w is a neighbor of v, and it's the ith neighbor of vertex v. Not only that, but if I go to vertex w, then since the graph is symmetric, v should also be somewhere here, right? If v comma w is an edge, w comma v is also an edge. So v is also a neighbor of w, right? But what neighbor is it? It's neighbor j. Okay, it's kind of a double indexing, right? Not only is w equal to jth element in this list, it also gives a quick access to how to get to v from w. Okay, so ith element in this list, and this is the jth element. Okay. And a consistent labeling is basically a rotation map where you require that I equal j. So if W is the ith neighbor of V, then it should be that your labeling is consistent. Like, I call you the ith neighbor, then you should call me the ith neighbor as well. Okay. But it's not strictly required. You can have different labelings. Okay, does it make sense? Any questions about it?
I have a question.
Yeah.
So, is this rotation map like taking the undirected edges and in some sense viewing them as directed and like mapping the two different ways to traverse the undirected edge as directed edges?
So it is still going to be, that's one, you can define rotation maps for directed graphs. That's a good point. But here, this consistency that when we say W is a neighbor of V, V is also a neighbor of W. That's why we're kind of enforcing the undirectedness indirectly.
Right.
Okay. So even though it's in some sense we are saying W is the ith neighbor, we are also requiring that V should be a neighbor of W. So that's why it's like a undirected graph. Okay. So maybe let me just draw how a rotation map can slightly differ from. I can say this is 1, 2, but maybe this is like 2, 1, right? So I consider this to be my first neighbor, but this vertex considers me to be its second neighbor. That's fine. As long as everyone has their own labeling, it's okay. And so on. Okay. So we're relaxing the consistency constraint a little bit to allow for easier definition. All right. So now we can define the zigzag product as basically a pseudocode. If you think of this as some, kind of function which takes the rotation map of G, rotation map of H, and gives you the rotation map of the zigzag product. Okay. It's an ND D1 squared graph, and given the rotation map of G, and the rotation map of H, I'm going to tell you how to compute the rotation map of the zigzag product. Okay. And here, just for convenience, you can also change it to usual numbers, but we can think of these numbers from 1 through n times d as a pair. First one from 1 through n, second one from 1 through d, d1 squared also as two numbers, right? So this is basically subdivided into something like this. Like, cloud index and within cloud index. And this is the first edge label and the second edge label. Okay. So what is my map? How do I compute it? I take V comma A, which is the label of the vertex, K1 comma K2, which are the edges, and I compute the I first apply the rotation map of H to take the within H cloud step. Okay. And then I take the across cloud step with label A prime to get something else wherever I end up at. And then first cloud step across cloud. And then we take another within cloud step, right? Okay. So you compute these three things and then you output the vertex that you end up is at W comma B. And so this is why you don't immediately get a consistent labeling. Okay. I think it's clearer when you do 2 comma 1. Right. So let's think of this guy. So when we went from V comma A to 2 comma 1, we ended up here, right? But if I take 2 comma 1 from C, I don't end up here because I had to first take the 2 thing and then I take the B hedge off. So what should I do from here to get to here? What's the label? I need to reverse this thing completely, right? So 2 comma 1 got me here. 1 comma 2 will get me here, right? So that's a small change. You know, I take K1 comma K2 from here, but that's basically K2 comma K1. I need to reverse the steps from the other vertex. So that's why we look at rotation maps instead of consistent labelings, which is K2 comma. Okay. So I ended up vertex W comma B, but I am W comma B's K2 comma K1 label edge. Okay. Any questions about this? Yeah. Go.
Why did we use H rotation map for the first cloud step and not B?
So because we are within taking it just step within the cloud. Okay. As I said, you know, intuitively it kind of seems weird to do this, but the conceptual idea is somehow we want to define the edges so that my final graph is very well connected, right? So if I'm here and I immediately hop across, then I'm not connected to vertices within my cloud. So I have to connect myself to things inside first, right? So I take a hop and then I go across clouds using G and, you know, again, take another step there. Okay. So this taking 2 steps in clouds, that's basically like squaring, right? But we in between, we are interspersing it with like this G step, and that's where we're going to get. Okay. So that's why it's like, you know, we looked at squaring, which was improving the spectral gap and connectivity, but was costing in the degree. So here we're going to win because the degree of H, D1, is going to be much smaller than the degree of G. So you should think of G as being like a very high degree, H a small degree, and we're kind of taking a square step in H by taking a big step in G. Okay. We'll see the intuition play out in the analysis in a second. Yeah, you had a question?
Yeah.
So there's going to be the spectral gap. We have to control the spectral gap in the end. So we won't get an exact formula for what the spectral gap is, but we'll get an upper bound on it, which is going to be enough for the analysis, right? So our motivation again is to define an analog of squaring the graph. Squaring the graph had this nice thing that it squared the second largest eigenvalue, which made it smaller because it was like 0.9, it's now 0.9 squared, 0.81, right? So it's decreasing it. Was costing too much in the degree. So we're going to say that zigzag product is going to do something similar. The second largest eigenvalue of the zigzag product is going to be better than both of the graphs, actually better than definitely that of G, but the degree is going to be much smaller than squaring G. Okay. You had a question? Purple edges, yes. Yeah. Yeah. Right. So this is saying rotation map H of A comma K1. So take the edge labeled K1 out of vertex A in the graph H. You end up at a vertex A prime, okay? And A prime is like, what is A correspond to A prime? A is the I primeth edge out of A prime, okay? We are not going to use this for now. It's basically like saying here, right? I took the second neighbor out of A, I ended up here. But when I end up here, A should also be listed somewhere here. What is that number? That's going to be I prime. We are not using it, at least in this construction, but later on in other steps we do use. Okay. It is very clever definition. It took people a long time to come up with this. And it's very, very beautiful. It's just 3 steps in some sense, but very influential. Okay. All right. So let's see what this actually buys us, right? The punchline, I should say, is the following. Okay, so qualitatively, small lambda is a good graph. Small degree is a good graph. Of course, we want to kind of compare them to each other. I can easily square and then get small lambda, but my degree is also increasing, right? We want both of them to be small in some sense, okay? And what zigzag essentially does is you inherit the number of vertices from G. You almost inherit lambda from H instead of G. Okay? And you also inherit the degree from H. The only thing that you're going to get from G is kind of the number of vertices. It kind of allows you to scale, but keep the good properties of H more or less. Okay? So this is the main theorem. So the quantitatively sharp thing that we are going to show is due to Rosenman and Vadan from 2005. The original paper, which defined zigzag product, had a slightly weaker bound with a more complicated analysis due to Reingold, Vadan, and Wigderson. And so it's an ND D1 squared, comma lambda graph. Okay, let me call this graph F, where lambda is the following. Okay, it sounds like looks like a weird equation, but so lambda is at most 1 minus lambda squared times 1 minus lambda G, right? So to get a sense of this, you should think like, okay, what's happening here? Okay, so at some point, once lambda G becomes small enough and lambda H is small enough, this new graph will also have small spectral gap, right? But instead of but the number of vertices is still very big, and the degree only depends on H. It doesn't depend on G's degree at all. Okay, So that's what like really helps us in kind of really bootstrapping the kind of controlling this trade-off between degree and lambda. Okay, so we'll increase lambda by squaring first, which will hurt the degree. We'll bring down the degree using zigzag product without hurting the spectral gap, and keep on repeating this. Okay. But as I said, you know, for now, just think that it helps us control lambda in a nice way while not paying something which depends on the degree of G in the new graph. It only depends on the degree of H and not on the degree of G. Okay. So let's take a 5-minute break. And when we come back, we'll prove this. This involves linear algebra. The first part is kind of really rolling up your sleeves and following the equations exactly to compute what the adjacency matrix of this graph is. Okay. It turns out, even though the definition looks like all of this rotation maps and look pretty complicated, the adjacency matrix of this graph has a nice compact formula for it. Okay. And then we'll use that to compute the eigenvalues or get some bounds on the eigenvalues. Okay. So let's take a 5-minute break, and when we come back, we'll do that. So the definition of this zigzag product is kind of combinatorial, has some intuition that I want to kind of take steps within cloud to mix myself in the cloud, to give me a chance of getting to every place within each cloud, and then also give me a chance to jump across clouds as well as G does, right? The analysis is purely linear algebraic, okay? And you'll see, even though it just fits into place very well, but you have to do the calculations, right? I'll do some of them. I won't do everything because you just have to stare at them and convince yourself. They're not complicated, but you have to convince yourself that this is what it is, okay? All right. So we want to understand what is the second largest eigenvalue of F. Seems very complicated, right? You know, you have this graph. Right now, it's a complicated thing. It's defined by this algorithm, more or less, of computing the rotation map. How can I figure out the spectral properties of it? Well, to figure out the spectral properties, let's ask ourselves, we should first try and figure out what is this adjacency matrix? What is this normalized adjacency matrix? Because that's what we need to compute the second largest eigenvalue, okay? So the writing down the adjacency matrix is F of F directly is complicated, but there's a nice way to break it up, okay? And we can draw inspiration from what happened for the square of a graph. For the square of a graph, the adjacency matrix was literally the square, because in some sense we said, okay, I'm taking one step and then another step in the same graph, right? So G squared became the adjacency matrix of G squared was just adjacency matrix of G whole square, okay, a product of it with itself. Something similar happens here, right? So we'll break up the adjacency matrix into 3 parts. So this is our graph, and we want to figure out what is the adjacency matrix of F. And to get a sense of what the adjacency matrix is, well, first let's figure out what are its dimensions, right? Its dimensions are n times d by n times d. The number of vertices is n times d and n times d. Okay. And what would be one way to view this adjacency matrix, which will be helpful? You know, how would you start writing down the vertices? You have nd vertices here, right? And nd vertices. Given the way we define the graph, how should I view this matrix? Any suggestions? I want to say there's one natural way which will help us significantly in understanding what this matrix looks like. So how should I number, in some sense, the rows and columns? Well, the definition of zigzag uses clouds, right? So we can group these vertices into clouds, okay? And we'll view it essentially more or less like a block diagonal, block matrix, and try and figure out what each block should be, okay? So So we are going to view the matrix as divided into blocks. Each block corresponds to a cloud. Okay. So for instance, all of these correspond to 1, A, 1, B, 1, C, 1, D. Right? These are the vertices. This is 2, A, 2, B, 2, D, and so on. I mean, this is assuming H has 4 vertices, of course. In general, you'll just have 1, capital D, and so on. Okay. We have to figure out, we'll figure out what are these blocks in some sense. Okay. And let's once again think about how we are generating this graph and build the adjacency matrix from there. So there's a zig step, which is the first within cloud. There's the across cloud step, and there's the zag step, which is another step within a cloud, right? Suppose I didn't have the other two. I only did the step within the cloud. What would the adjacency matrix look like? Again, this is a thought experiment. We're going to put everything together. But suppose I did not do the across cloud step and the second within cloud step, just the first within cloud step. Yeah? Exactly, right? Because, if I'm not doing any of the across cloud steps, I just have isolated copies of H everywhere. So what would I have in that case? If I only did that, maybe I shouldn't draw it this way because that gives the wrong impression. This is the kind of thing where if someone told you there is a clear, precise formula, then you can figure it out, but you have to somehow believe that there is such a formula, okay? So if I just had only the within cloud step, I would only have the isolated clouds, right? And those will just mean that if I go back to this representation, like all of these would be 0. Right? No clouds, no edges across clouds, and within each cloud, I just have the copy of H, right? So what would that matrix look like? The adjacency matrix of H on this diagonal blocks and zeros on the off diagonals. Okay? You believe me with this? Right? And if I only had the last step, which is the zag step, and nothing for the mixing between the clouds, what would that be? Yeah. Flip, but in fact, because we're rotation map, let's say it's consistent for now, it's exactly going to be the same. Okay. You have to be a little bit careful with the rotation map, but essentially the same thing. Okay, you should think of this as like what the zig step is doing, and this is what the zag step is doing. Okay, but there's a within cloud, across cloud step, we need to figure out what it's going to do. Okay. Right. So what is the across cloud step going to do? Well, so we don't have these edges anymore. I mean, or at least we're not worrying about it. We're only worrying about what the green edge is going to do. How many green edges can a vertex have here? How are we defining the green edges? We said wherever you are, like let's say I'm at V, D, I have to take the dth neighbor out of V and connect it to wherever I end up at. Okay. So the green edges are really like each vertex will have exactly one green edge, right? Because they're deterministic. You had some flexibility in choosing which edge to take in a cloud, There's like, 1 through capital D1. And again, here also you had options 1 through capital D1, but across clouds, you don't have options, right? If I'm here, where would the green edge take me? For example, this is V comma C, right? So I have to go back to this graph and see, oh, C took me here, right? And because it was consistently labeled, it would just take me to this. Okay. So the green edges are such that every vertex has a single green edge going out of it. Okay. So if I write down the adjacency matrix of such a thing, what will it look like? Every row, it's like a degree 1 graph. Every vertex has single green edge. It's a degree 1 graph, right? Okay. And this is the part that requires some convincing, but if you follow the equations, it works out that way. And this is the part that's actually not like, we'll have non-zeros everywhere. Okay. Like, it can have non-zero entries everywhere, but there can only be one non-zero entry per row because each vertex only has one green edge. Okay. So this is the intercloud step. And this is a permutation matrix. As determined by G. Okay. And we kind of know exactly what this matrix is too. We can say, I'll call it P. If I take some entry V comma A here, and a column entry W comma B, when will it be 1? So when is there an edge between them? Well, if and only if the rotation map of G took V comma A to W comma B. Okay, it's kind of a matrix representation of the rotation map, right? So if I took the 8th edge out of V, I need to end up at W, and that W should be the bth edge, and my V should be the bth edge out of that, if and only if. Okay. Yeah.
Using our labeling scheme, technically A and B should also be the same. Right?
Yes. I mean, initially, so when we compose this, because K1 comma K2 became K2 comma K1, we lose the consistency labeling after the first step. Even if I start with G and H being consistently labeled, zigzag isn't consistently labeled afterward. That's why we define this generally so that we don't have to worry about it. There is a way to make everything consistently labeled again and so on, but in the recursion it gets super complicated. It's not worth the trouble. Okay. But you're right. When I start with consistently labeled things, A should equal B, and it's even simpler there. Right? Yeah. So this matrix is symmetric in the sense that if this is these two are connected, then the other way is also connected. And that's actually kind of implied by the rotation map property, right? All right. So now this is the beauty of representing graphs by matrices. I'm taking 3 steps and connecting the final 2 endpoints, right? And I kind of know the matrix representation of each step. So how do I put them together to get the final graph? You multiply them, right? Just like for square, it was like you're taking a step in the first graph, taking a step in the same graph. The way we put together is multiply them, right? So the adjacency matrix is just going to be this. Okay. So even though, I mean, the entries are complicated, but there is this almost very clean representation of what the adjacency matrix is as components. is a product of three matrices. The first two are just blocks of A's on the diagonal, zeros everywhere. The middle one is the G step. Okay. So this is a claim. The adjacency matrix of F has this compact representation. Let me call this PG. And this matrix itself can be written in a compact way using tensor products, right? So if you haven't seen tensors, I'll talk about that in a second. The only thing that we need about that is that the eigenvalues of this matrix are very easy to get, right? They're basically zeros. They're inherited from the eigenvalues of H, more or less. And eigenvectors are also kind of inherited essentially from H, okay? So this matrix is the identity matrix on N times AH. What is this times? This circle times is the tensor product. Right? And so if I have a matrix A, which is D1 by D1, let's say. No, okay, if I have these two matrices, N1 by N1, N2 by N2, then A tensor B is just the matrix where I put multiple copies of B together. Okay, so this is the matrix N1 times N2, N1 times N2. Okay, I'm putting copies of B in blocks, but I'll scale each copy of B with the corresponding entry in A. So this will be A11 times B, A12 times B, A13 times B, and so on. Okay, so that's how you define tensor product. Like, you have the numbers here, and replacing each number with a copy of B times that number, kind of expanding. Okay. So in particular, if I do the identity, then when the off diagonal things become 0, whereas on the diagonal, I'll just get the same matrix. Okay. All right. And so we have the adjacency matrix is this guy. And what about the normalized adjacency matrix? Well, to normalize the adjacency matrix, I just need to divide the adjacency matrix by the degree. What's the degree of F? D1 squared. I need to divide it by D1 squared. But what would be a nice way to do that? I should split that D1 squared as D1 here and D1 there. Okay. So that way, what I get is just the normalized adjacency matrix of H, PG, and normalized adjacency matrix of H. Okay. Any questions about this? Yes, no? Okay. So now we have at least a compact and clear formula for what the adjacency matrix is. And we should now try and figure out what the second largest eigenvalues are. One thing to keep in mind is, matrix products usually don't behave well with eigenvalues, right? If I have some matrix A and matrix B, if I multiply them, the eigenvalues of A times B might not have anything to do with the eigenvalues of A and B. There's no like simple formula for connecting them. But for these special matrices, given that you have like identity here, this is a permutation matrix, we can get some control on them by using linear algebra. Okay. All right. So how do we do this now? Okay. And here's linear algebra lemma 1 that we need. Again, this is something that you can prove by using the eigenvalue decomposition theorem. And I won't prove it, but if you're interested, I can tell you how to prove it by using the eigenvalue decomposition theorem. So suppose I have a graph, right? So it could be H anything really, it doesn't matter. H is a, it doesn't matter, it's true for any graph, just forget whatever that is. Okay, suppose I have G, which is an ND lambda graph, meaning its second largest eigenvalue is at most lambda. It's a D-regular graph. Now, for any D-regular graph, we do know that its largest eigenvalue is 1. The all ones vector is an eigenvector. This is something that we already showed, right? Other than that, we usually cannot say much about the other eigenvectors. They can be all over the place. There's no structure in them. There's like, if I just know the degree, I might not be able to say anything about that. But I do know that the second largest eigenvalue is lambda. Okay, that's what we know. But it turns out that this already gives you something. So it is true if and only if I can write the normalized adjacency matrix as I'll talk about what this means in a second. So to interpret this, just recall the eigenvalue decomposition theorem, right? So eigenvalue decomposition theorem says that any symmetric matrix can be written as like the eigenvalues times the eigenvectors, right? So I should be able to write this as lambda 1 times V1 transpose plus lambda 2 times V2 transpose plus so on. Okay, where these are the eigenvalues and VIs are the eigenvectors which are orthonormal. They have to be unit norm and are perpendicular to each other. Okay. Now, for MG, we know that the first one is a 1 and all ones vector is an eigenvector, right? But we need to normalize it so that its L2 norm is 1. Okay. So this is going to be 1 times the vector which is 1 over root n, 1 over root n, all the way up to 1 over root n. Okay. Right. So this is the all ones vector scaled so that it has length 1. Okay. And then you have all of this other stuff here. Right. And I can think of this as 1 times 1 over n times the all ones matrix. Okay. And we'll call this Jn. Jn is just shorthand for the all ones matrix, which has n rows and n columns. Plus lambda 2 times V2 transpose plus so on lambda n times Vn transpose. Okay. We don't know much about this V2s and V3s and so on. All we know is that all the lambda 2s are at most lambda in magnitude, and they're orthonormal. The V2s are orthonormal. I can further decompose this as 1 minus lambda times Jn over n plus lambda times Jn over n plus lambda 2 times V2 transpose plus so on. Okay. So why am I doing this? In some sense, we are going to approximate mg just by the leading term here. And think of all of these things as error terms. Okay. The first eigenvalue is the most important, and everything else we're going to kind of view it as error in our approximation. I mean, of course, you need to make sure that how this error behaves with others and how good this approximation is soon, but that's what we're going to try and do. Okay. So I'm going to call this matrix E. Okay. And what's the largest eigenvalue of E? Actually, let me call it lambda times E, because the scaling will help. So if I call it lambda times E, what is the largest eigenvalue of E? Well, in fact, what are the eigenvalues of this matrix? The eigenvalues are going to be lambda, lambda 2, lambda 3 up to lambda n, because I gave you the eigenvalue decomposition, right? I don't have to tell you the eigenvalues anymore. I gave you that it's a combination of these orthonormal vectors. So the eigenvalues are exactly going to be lambda, lambda 2 up to lambda n. And none of them are at, all of them are at most lambda in magnitude. Okay. So that means that if I define this norm for a matrix, which is called the spectral norm of a matrix, as the largest absolute eigenvalue of a matrix. This is called the spectral norm for symmetric matrices. If it's not symmetric, you have to look at singular values, but that's okay. Okay. So for a symmetric matrix, the spectral norm is the largest absolute eigenvalue of the matrix. If I define it this way, when I put these things together, the largest eigenvalue is at most lambda. So I can write it. This statement makes sense. Okay. If the second largest eigenvalue of mg is at most lambda, then I can write it this way, where 1 minus lambda times Jn over n plus lambda times some error, where the largest eigenvalue of E is at most 1. Right? The if and only if part is more complicated, but it's also true. The other direction is also true, but we won't really, we need it, but let's not worry about it. Okay, we're going to take it for granted. So when I say it's a spectral norm, it's a non-trivial thing to prove, but you can actually prove, again, wonders of linear algebra. Just like the first wonder of linear algebra is that row rank equals column rank. The second wonder is that this is actually a norm. So if I have two matrices which are symmetric, you can again define things for non-symmetric too. Then what does it mean to say it's a norm? Well, if it is a norm, we need to have triangle inequality. The norm of A plus B is at most the norm of A plus the norm of B. Okay, so it's saying the largest absolute eigenvalue of the sum of two matrices is at most the sum of the largest absolute values of the A and B. Okay, it requires a proof, but it can be done. And moreover, it's kind of also is multiplicative. It's something we Yeah, if A times B, then it's norm of A times norm of B. And finally, for tensor products, also, in fact, it's exactly true. Okay. So the norm behaves exactly almost like the absolute value, right? If I had take the absolute value of numbers, absolute value of A plus B, that means absolute value of A plus absolute value of B, it would be an equality here, but we have a less than or equal to. But tensors, it's an actual equality, even though we only need one direction for the most part. Okay. The last one is kind of easier to prove than the first two, even though it seems trickier, because the eigenvalues of A tensor B are just a product of the eigenvalues of A and B. So you know the exact formula. These two require a bit of work. Okay, but we're not going to prove them. We're just going to use these facts from linear algebra. Okay. And so we have two linear algebra lemmas. We need one more, which is that for any permutation matrix, permutation matrix just means that every row has a single one and everything else is zero. Every column also has a single one and everything else is zero. Okay. For every permutation matrix P, its spectral norm is actually just one. Okay. So one way to prove it is to show that permuting rows and columns doesn't change the spectral norm. And if you take the identity, then all the eigenvalues are one, so it's exactly one. Okay. So these, lemma 1, lemma 2, and lemma 3 are going to be our sort of levers to compute or get bounds on the second largest eigenvalue of this matrix. Okay. In particular, we'll use the if and only if part. We'll show that MF can be written in this way, where there's a small error compared to some term, and that term will give us whatever bound we were shooting for. Okay. All right. So how do I proceed now? Well, this is where, as I said, you had to work through some of these equations. Okay. Let's painfully work through some of them, and then we will see where we end up. By lemma 1, I can write this adjacency matrix of H as 1 minus lambda H times JD by D plus lambda H times EH, where EH is less than. Okay, I'm just using lemma 1 applied to the adjacency matrix of H. Again, we are going to basically view these as error terms. Okay, and these JDs will be the right things that we need. So what is the tensor product of these things now? Tensor product is associated with addition. Okay, so I get 1 minus lambda H times IN tensor JD by D. Okay. So if I put these two together, I have MF is this massive expression with me so far? Right? Now it looks very cumbersome that you have all of these things, but as I said, this is what it is. You have to work through it. Okay. And there's really no way around this except having to just multiply this thing out. Okay. If I multiply this thing out, I have like 1 term, 2 term, and then I have term 3, term 4. I'll get 4 terms. Okay, so I'll get 1 minus lambda h whole squared times okay, and then a bunch of other terms like this is some tedious calculations, but you'll see it doesn't get too much worse, luckily. Then the last term is just okay. We have 4 terms, and as it turns out, we can easily control these 3 terms. Okay, let me call this one error 1, this one error 2, this one error 3. Okay. So let's look at error 1 term. So what is it? It's 1 minus lambda h times lambda h times this seemingly weird looking product. Okay. And if you want to control the error terms, you want to control the spectral norm of those error terms. So if I put spectral norm here, I get spectral norm. And any suggestions on how I might proceed to manipulate this? We don't have to be too inventive here. In some sense, we already won because we have this 1 minus lambda h times lambda h. And we're just going to use the this inequality. That spectral norm only multiplies, or you can upper bound it. Okay. And well, now what? This one, we know what the spectral norm of tensor products is. It's a product of the spectral norms. This is a spectral norm 1. This is a spectral norm 1 as well. So we get this is at most 1 minus lambda h times lambda h times 1. Permutation matrix, spectral norm is 1. And this is also 1 because EH has spectral norm 1. Okay. So the whole thing has spectral norm at most 1 minus lambda h times lambda h. Okay. And if you do the same calculations for E2 and E3, you get the same bounds. Okay. Similarly, Okay, so I'm almost out of time today, but let me end at a point where we can finish. So why is PG a permutation matrix? That's a good question. If you go back to the definition of the PG here, and you can see that every row has a single one and every column has a single one because of the way rotation map is defined. It's a one-to-one bijective mapping, and that's the reason why we get it's a permutation. Okay. Okay. So if you put all of these things together, what happened? So we know that MF is equal to we sort of have this leading term, and then we had the error terms E1, E2 plus E3. Okay. Let me put all of these things together and call it E. The norm of E is at most the spectral norm of 1, spectral norm of 2, plus the spectral norm of 3. Okay. And this is, if you simplify it, I think you can equal to this. Okay. All right. So we made some progress in that I can write down MF as some matrix which has, some reasonably simple form, a matrix which does not depend on H anymore, right? So we gain something there. So there's no more H in the first term. So at least it's a simpler matrix for us to understand. And then we have some error term, but we can control the error term as this, right? Particularly if lambda H is very small, like let's say it's 0.1, the error term has very small spectral norm, like 1 minus 0.9 squared, that's going to be 0.2 and so on. Okay. As lambda H becomes close to 0, the norm of the error also gets close to 0. Okay. So when we come back, we will try and understand the first term. And turns out the first term also, linear algebra gives you a good way to write it. We just had to figure out what this JD times PG times JD is. And that's where the spectral gap of G shows up. Okay. All right. So let me stop here and we'll finish this in the next lecture and then see how to use it for the connectivity problem. Okay.